and welcome to the Math Week 14 review for Math 2413. In this review, we'll be touching briefly on finding the area between two curves, just a really quick review, but mostly we'll be talking about the washer method and the shell method, so two methods of finding volume by revolution. So let's jump right in. All right, first off, just a quick review of area between two curves. If you'll recall, we have a nice formula for area between curves. And that formula is simply the integral from some starting point to some ending point. It could be the intersection points of our curves. It could just be two arbitrary values we're given. And then all it is, it's going to be the top function minus the bottom function. So that's our general formula. So let's do a quick example with this. Let's say we wanted to find the area between f of x is equal to the sine of x and g of x is equal to 0 on the interval from x is 0 up to 50 pi. So if we sketch out just the first little bit of this graph, here we have our sine x curve, and here's our line 0. So the area that we're looking for is going to be all of this plus all of this. And we're going to have this repeated a whole lot. Right, so we would have this repeated 25 times because this is 2 pi. So it would be this, then paste it again, gives us 4 pi, and again, and so on.
Could we also just take the first one and multiply by 50?
Right, so we're actually just going to take this first area because we can say, I know that this area is actually the same as this area. So what we're going to do is we're going to take this first area, which we can represent as the integral from 0 to pi. Our starting point is 0, our ending point is pi, of our top function, minus 0. And we're going to say that the total area is just going to be 50 of these. So we're going to multiply it by 50.
Why do you subtract by 0?
Because 0 is our bottom function. So here we have our top function. Down here we have our bottom function.
Oh,
so I'm just really explicitly saying our area between two curves is our top function minus our bottom. Yep. So this gives us 50 times the integral of sine is negative cosine. Again, we have from 0 to pi, which gets us 50. The cosine of pi is negative 1, so negative 1 is positive 1. And here we have minus the cosine of 0 is positive 1. It's negative, so negative 1. 1 minus negative 1 is, of course, 2, so we have 50 times 2, which gives us an even 100. That makes sense? All right. In that case, let's just go ahead and move on. Area between two curves is fairly straightforward, so if you do have any questions, just let me know, but if not, we're just going to move on. Okay, now let's get into some volume by revolution. This stuff is super fun. And we'll start up by talking about the washer method. You might also hear it called the disk method. They're basically the same thing. The washer method is a bit more flexible though, so I'm just going to teach that. If you know the washer method, you also know the disk method. So let's say we have some kind of curve. I'm going to draw something really simple. It's going to be a shape kind of like this. And I'm interested in making a shape by spinning it around this axis here. Well, when I spin it around this axis, what I'm going to get is I'm going to get this kind of weird looking shape kind of like this. And then I have my inside part, and my inside part here as well. And I'd also have that going down to there. And this line goes around. So I'm going to get some kind of like weird, not quite filled cone with the top lopped off. Basically just a shape that I've made by spinning this original curve, which I should probably outline in red, around this horizontal Y line that I decided to spin it. Well, how can I find the volume of this shape? That's the question I want to ask myself. Well, to do that, I'm just going to look at a single cross section of this shape. So you can imagine just taking a knife or something and cutting the shape right there. And when we look at it from the side, what we're going to get is we're going to get a perfect circle with a hole cut out in the middle. So you can think about this distance here becoming this distance right here. Well, I can really easily find the area of this shape, which is all of this. And the way I can find the area of this shape is just by taking the area of my large circle, which I'm going to call capital R, taking the area of my smaller circle, which I'm going to call lower r, and subtracting them. So the area of my large circle is pi times capital R squared. The area of my lower circle is pi times lowercase r squared. And then I can just factor out my pi, and that's where I get my nice r squared minus 4r squared. So this is the area of a single circle. In order to find the volume of my whole shape, what I can do is I can just take this area and actually just integrate it along this whole distance here. So my volume of my shape, I can say, would be the integral from some starting point to some ending point of pi times this capital R distance squared minus this lowercase r distance squared. And that would give me my volume. So that's kind of where my formula comes from. If you want a slightly more technical explanation as to why we're doing the integration, the idea is that we're almost just like stacking a series of cylinders. So we would first approximate our shape using, if I could draw a lot better, like a series of cylinders that we've stacked like this, and then another one right on top of it, like this, and then another one on top of it like so, and then we just increase the number of cylinders. That's kind of the intuition behind what we're doing. So when we let the width of each cylinder go to 0 and have an infinite number of cylinders, we'll have a perfect approximation. The shell method has the same cylinders in a different way, so we'll get to that later on. But this is the washer method idea. And this is kind of where our whole formula comes from. So as long as you can sketch out a nice picture and figure out what your capital R and your lowercase r should be, so what your outer radius and inner radius are, then you can set up your equation and solve your problem. So let's go ahead and do an example. What I want to do is I want to rotate the region bounded by y equals to 2x plus 1 and y equals to x squared minus 2 about the line y equals to negative 2. Well, first off, I'm going to try and sketch a picture. I know that the line y equals to 2x plus 1 looks something like this. It's got a y-intercept of 1 and a slope of 2. So I'll go ahead and sketch that in. And I also know that y equals to x squared minus 2 has a y-intercept of negative 2, and other than that, it's just a pretty straightforward quadratic. So I'll just sketch them both. Okay. Well, first off, I'm going to want to find these intersection points. And also, I want to sketch in the line that I'm rotating around. So here's the line that I'm rotating around. I'm going to go ahead and mark that as well. So let's find the intersection points because I need to know where my integral should start and where it should end. So to find my intersection points, I'm just going to set my two equations equal to each other. If I move all the terms over to one side, I get that x squared minus 2x minus 3 is equal to 0. I can factor that into x minus 3 times x plus 1, which tells me that x is either equal to -1 or +3. So I'll just mark that on the graph, and that'll give me my lower bound and my upper bound for my integral. Now I need to figure out what my capital R and my lowercase r should be. So if you'll remember, when we took the cross section, here we had, this is the center of our circle, this is the distance of our small r, because this would be like a smaller circle right there, and this would be our larger r, so this distance from here down to here is our larger. And I should just go ahead and mark that on there. Whoops, that should be a lowercase r. So in this case, I'm looking for two distances, my capital R and my lowercase r. My lowercase r is going to be the shorter distance from one curve to my axis of revolution. So right here, this would be my lowercase r. And I can find the distance from this y equals to -2 line to y equals to x squared minus 2 just by taking the top and subtracting the bottom. Let me double check that really quick. Yep. So I take my top function. The one on top is x squared minus 2. And when I say top, what I'm doing is I'm only focusing on my axis of revolution and the function that I decided would make up my little r's. So I look at the one that's just higher vertically of those two, which is x squared minus 2, and then I subtract the other. So minus -2. And that would get me x squared minus 2 plus 2 is just x squared for my lowercase r. Now for my uppercase r, my larger radius, I take a look from my axis of revolution to my further function. And again, I just say, of my further function and my axis of revolution, which one is higher? Well, it's going to be my further one in this case. So 2x plus 1, and then again, I subtract -2. So right here, I've got my capital R, and right here, I've got my lowercase r. So I'm ready to go ahead and integrate. Once I simplify this, this becomes 2x plus 3. Okay, so my volume, I know my starting point is going to be -1. My ending point is 3. My capital R is 2x plus 3. So I'm going to square that and subtract my lowercase r squared as well. And from here, it's just algebra and solving this integral. So I'll go ahead and work through that. We're going to have -1 to 3. First, I'm going to square my terms and distribute. So that's 4x squared plus 12x plus 9 minus x to the 4th dx. Here, none of my terms will combine, so I can just go ahead and integrate. And this would get me 4/3 x cubed plus 6x squared plus 9x minus 1/5 x to the 5th from -1 up to 3. And when you plug in your bounds, this comes out to be 1088 pi all over 15. Any questions as far as this problem? All right. In that case, we'll go ahead and do a practice problem for you. find the volume of the shape created by rotating the region bounded by y equals to negative x and y equals to x squared about the line y equals to 3. I will give you guys a few minutes to work that one out. Good luck. All right, you got 13 pi over 15. That is correct. Good job. So we'll go ahead and run through the problem anyway, for the benefit of anyone watching. Let's see. So as soon as OneNote catches up with me, what I'll be doing is I'll first try and sketch a picture of my region so that I can use it to figure out what my capital R and lowercase r should be. And then I will be finding my intersection points as usual, figuring out my capital R and lowercase r, and then just plugging that into the formula that we already discovered earlier. There we go. Okay, so first off, we'll try and sketch our region. Because I've done this before, I already know what it looks like. So here's the line y equals to negative x. Here's the line y equals to x squared. Like this, roughly. That's not the prettiest parabola I've ever drawn. Here's our intersection points, which I happen to know are at -1 and 0, but I will calculate those in a minute just for everyone's benefits. And here's the line y equals to 3, which we are rotating it about. So here, right here is my region. And I'm using the washer method. So first off, to find my intersection points, I will just set my two equations equal to each other.
You also solve for that other thing that's just below y equals 3.
Sorry?
But you also solve for that other thing that's just below y equals 3.
This part?
Yes.
In this case, no, it's not the region bounded by these two lines. So we're looking just at y equals to negative x and y equals to x squared. So this part, this line doesn't count as a boundary line. Yeah. Here's my setup for finding my intersection points. I can move my x over to the other side. So then factoring gets x times x plus 1 equals to 0. So x equals 0 or x equals to -1. And that gives me the same boundary points that I already marked. So now I just need to figure out what my capital R and lowercase r are in this case. So my short radius would be from here to here. And I can see that that's just going to be my top function, my y equals to 3, minus my y equals to negative x. So little r is equal to 3 minus negative x, which is equal to 3 plus x. Also, I'm going to have a capital R, which would be the further distance from my axis of revolution to my other function. And that's going to be, again, 3 minus, here I just have x squared. So 3 minus x squared. And now I can go ahead and write my formula. So my volume is going to be pi times the integral from -1 up to 0 of my capital R squared, so 3 minus x squared minus my lowercase r squared. And now I can just solve my integral. First I'm going to distribute, so this gives me 9 minus 6x squared plus x to the 4th minus, and here we have 3 squared is 9, minus 6x minus x squared. Now I'm going to order my terms like so. So I have x to the 4th, and I have minus 6x squared minus x squared minus 7x squared. I have minus 6x, and I have 9 minus 9, which cancels. Now I can go ahead and integrate. That should be an x to the 4th. I miscopied it. That'll get me 1/5 x to the 5th minus 7/3 x cubed minus 3x squared, all from -1 up until 0. All my 0 terms are going to vanish, so that leaves me with pi times negative, and here we have -1/5 plus 7/3 minus 3. Distribute the negative, and that gives me pi times 3 plus 1/5 minus 7 over 3, and that does in fact come out to 13 pi over 15. Any questions? All right. So again, just a quick recap. What we did is first we created our sketch and found our intersection points by setting our two curves equal to each other. From there, we used our sketch to help determine our capital R and our lowercase r, or in other words, a longer radius, the radius of our outer circle and the radius of our inner circle. And once we did that, we simply took those and plugged them into our formula for our volume and solved from there. All right. Well, since everyone seems to have a pretty solid grasp on the washer method, we can move on to the shell method, which is also a cool method. So here we go, shell methods. And the shell method is another way of finding volume by revolution. In fact, it'll find the same volume in a lot of cases. It's just that sometimes one method works better than the other. So sometimes the washer method is going to be a whole lot easier to do, and sometimes the shell method is going to be a lot easier to do. So let's start with a picture again. Here we have just our x and y axis. Let's say we're rotating just about the x axis for simplicity's sake. And we have some curve like this. And we are interested in rotating this curve about the x-axis side. Well, what we can actually do is we can kind of build it by using a series of shells of cylinders in a different way. So if you'll remember from the washer method, what we did is we kind of put our cylinders together like this. And that's a perfectly good way to do it. The shell method, instead of putting the cylinders together like this, actually put cylinders together in, okay, this one's a bit harder to draw, like so. So if we have a horizontal bar right here, what we can do is we can turn this into a cylindrical shell right here. But instead of being a completely filled cylinder, what we're going to do is we're going to make it hollow. And then we're going to create our volume by filling this cylinder in turn with other cylinders. So instead of stacking the cylinders on top of each other, we're putting them inside of each other. So if we look at the volume of just one cylinder, well, we say this cylinder is hollow, like so. And because it's hollow, I'm going to say I want an easier way to find the volume than just taking the volume of the whole cylinder and subtracting the inside volume. What I'm going to say is if we look at just one part of the cylinder, then that part is basically going to look exactly like a rectangular prism. And these have a really easy method for finding the volume. We just do the base times the height times the depth. So if I took this cylinder and I cut it open, it would basically look like a big long rectangle with a teeny tiny bit of depth. So what I'm going to do is I'm going to say, well, the volume of this cylinder is equal to the area of it times its depth, which I'm going to call W. So the area would be the circumference of my cylinder. So the circumference, which would be 2 pi r, multiplied by this radius here. Sorry, that's not right. Multiplied by this height here, sorry. The height is this distance here. So 2 pi times the radius times the height.
Wouldn't the height be the long side and the radius be the short side?
My pictures are not very well drawn to scale, so it maybe would be kind of like this, but you understand we're kind of unrolling it, but yes. The general idea is one side comes from your circumference, the other side comes from your height. So all we're doing is, maybe if I trace out one edge, let's see, we'll go with green. If I traced out this outside edge of my circle, well, when I unroll it, I would start at my same point, one of my corners, and then I would just kind of roll my cylinder along this, and that gives me this edge. And then my height, which goes along the top, would just stay the same. So all I'm doing is I'm just kind of unrolling this empty cylinder. And I'm saying that the volume is almost equivalent to that of just a rectangle. It's not quite the same because we kind of, when we cut open our cylinder, it's not a perfect rectangle that we glued together, but it's almost the same, especially when we have such a small width that we're working. So what I'm going to do is I'm going to say, when we stack an infinite number of these cylinders inside each other and make them infinitely skinny, well, that's kind of our whole idea behind an integral. So using the shell method, what we're going to do is we're actually going to integrate, letting our w be our infinitesimal, our dx in this case. So in this case, what we get is we would have just integrating the area of this rectangle that we found to approximate the volume of our cylinder. So our volume would be the integral from some starting point to some ending point again of our area of a single rectangle. All right, so let's go ahead and do an example problem because this was all a bit abstract. But that's kind of the intuition behind where we get this 2 pi rh from. We're just integrating the area of a rectangular approximation for the volume of a single cylindrical shell. All right, use the shell method to find the volume of the region bounded by y equals x and y equals to x squared rotated about the line y for x equals to 0. Again, I'm going to start by drawing a graph. Here's my curve y equals to x. Here's my curve y equals to x squared. And this is the region that I'm interested in. I'm rotating it around the x-axis like so. Well, here, I'm going to kind of want to draw out one of my cylindrical shells, which would be right here. So the radius of this cylindrical shell would be the distance from here to here. I'll draw that in a different color so it's a bit easier to see. This distance here is my radius. Well, the radius is obviously just my y value. I'm going to leave that just as well. Now, I also need to know the height of my cylindrical shell. This distance here. Well, in this case, you'll notice that I can't exactly subtract my x values of my functions because then I'd have two x values. So what this kind of actually forces us to do is integrate in terms of y instead. So I'm going to let my h be represented in terms of my y values rather than my x values. So here I have y equals to x squared, or in other words, my x value is equal to the square root of y. And down here, y equals to x, so x equals to y. Well, this distance would be the higher x value minus the lower x value, or the square root of y minus y. that make sense?
Still kind of confused why you were saying you can't use X. I mean, I get why you don't, because you're rotating around the y-axis, right?
We're rotating it around the x-axis, yeah.
Oh, yes.
But the idea is, on this horizontal bar, x is not constant. So we want our variable to be constant when we're integrating it. Or I guess because if we had multiple different x values there, then it just kind of throws everything off. The idea is we want to measure this distance. How should I explain this? Give me one moment to collect my thoughts. So this h value is a distance, right? And because it's a distance, we need to figure out some way to represent that. But at this distance, the y value is, what was I saying? The distance is based off of the x values, right? So we need to take our top x value and subtract the bottom x value. Well, we can't represent that using just any general x value.
Oh,
Because if we represent it using a general x value, then we're suddenly like saying, well, we're trying to have x be any number because it's a variable, but also it's these specific numbers because it's representing your distance. So the idea is we want to use it, represent it using something a little more fixed.
Okay, that was the part that I was confused about when you said 2x, but now I understand.
Yeah. Okay, so here's our calculator, or our height. Yes. And now we have our radius and our height, so we can go ahead and set up our height. I'm going to move my 2 pi up front. Our r is y, and our h is root y minus y. And we also need to figure out our bounds of integration. In this case, because we're integrating with respect to y, it's going to be based off of our y values. So again, I would need to set my 2 functions equal to each other, except in this case, I need to use my y curves. So root y is equal to y because I'm integrating with respect to y. And if I square both sides, this gets me y equals to y squared. So y times y minus 1 is equal to 0, and y equals 0 over 1. So my limits are 0 to 1.
How come you plugged in y, just square root of y instead of y square root of y minus y?
So this is specifically this h distance here, but this curve is the line y equals to x squared.
Oh.
So x is the square root of y. Good question. All right, but now I have my function, and I can go ahead. Why isn't the height y square root y instead? I'm not quite sure how you would get y square root y. All I'm saying, like y minus the square root of y. Because my square root of y function, which is this curve, is my larger curve. So I'll just highlight this one. It's farther from my y-axis right here. So I'm saying that the distance from here to here is greater than the distance from here to here. So this one should be my top curve. So I always want to do larger minus smaller. Yep.
It's because your larger curve depends on the variable that you're using, correct?
Well, both your curves will depend on the variable you're using. In this case, looking just as to why I did square root y minus y instead of y minus square root y, I just said this curve has a larger distance from this axis. So it's just kind of to enforce that it's positive and I won't get a negative answer. Because if you flip them, your answer should just come out negative. But in this case, we're just trying to make sure that this h distance is a positive number. So to do that, I'm just using this distance. All right. I'm just going to distribute my y-ins. So that gives me y to the 3/2 minus y squared, which I can now integrate. So 2/5 y to the 5 halves minus 1/3 y cubed from 0 to 1. And that'll get me 2/5 minus 1/3, which is, I can use a common denominator of 15. So 2/5 is 6 over 15. 1/3 is 5 over 15. So 6 minus 5 is 1 over 15. Multiply that by 2 pi, I get 2 pi over 15. Sound good? And in this problem, it's actually just as easy to use the washer method. So I can really quickly run through the washer method for this problem. Here's my y equals to x line, here's y equals to x squared. In this case, my larger radius would be y equals to x. My smaller radius would be curve y equals to x squared. So I can set up this integral. Pi, my limits are 0 to 1. And I would have capital R squared minus lowercase r squared. And that would get me pi times the integral from 0 to 1, x squared minus x to the 4th, which gets me pi times 1/3 x cubed minus 1/5 x to the 5th, which is pi times, again I'd have 0 to 1, so just 1/3 minus 1/5. And 1/3 is equal to 5 over 15, 1/5 is equal to 3 over 15, so 5 minus 3 over 15 times pi, which would get me 5 minus 3 is 2, so 2 pi over 15, and you can see it's the same answer. So our shell method and our washer method do get us the same result, it's just that sometimes one is easier to do than the other. Any questions? All right. In that case, time to do some practice problems. We'll start with just one for the shell method. Use shell method. The region is going to be bounded by y equals to 2x, y equals to -2 times x minus 2, and the x-axis. I want to rotate it about the x-axis. And I will give you guys a few minutes to work through that. Let's see, you got 8 pi. Can you double check your answer for me? I think you're missing a term. Yeah, 8 pi is too large. Give it another couple of minutes, see if you can figure out your answer. Sound good? Or figure out your mistake. All right, let's go ahead and go over this one. So first off, we're going to want to set up a picture, of course.
Correct.
Yep, we're going to want to draw a correct picture. I'm going to draw it nice and large this time. So first off, we've got our curve y equals to 2x, which looks kind of like this. And we also have our curve y equals to minus 2 times x minus 2. So at x equals to 2, I know this is going to be equal to 0. And I also know that x equals to 0, it'll be equal to 4. So because it's just a linear function, I'm going to go ahead and graph that like that. So this is the region that I'm interested in, this little triangular spot right here. Go ahead and do some light shading so we're all on the same page. Okay, well, I'm rotating about the x-axis right here. Okay, so because this is the shell method, I'm going to use everything in terms of y. I can set up my little single cylindrical shell as an example, or as a help me set up my equation. So here's my single cylindrical shell. In this case, I might just represent it using just a single bar instead of drawing out the whole shell to keep my graph slightly less cluttered. But you can kind of see where it would go. There it is. And here I have the radius of my shell, and here I have the height of my shell. So in this case, I need to put my height in terms of my y values instead of my x values. So this top line is y equals to minus 2 times x minus 2. But I need it in terms of y. So this would be x equals to, I can divide both sides by negative 2 and then add 2 over. So 2 minus y over 2. And here, this line, my bottom part, would be y equals to 2x. Again, I need it as an x equals, so x equals to y over 2. So now I can write my height, which would be my top curve, this one, minus my bottom curve, this one. So 2 minus y over 2 minus y over 2. So I'll just label that top and bottom. And if I combine my y over 2's, I just get 2 minus y. For my r, in this case, again, it's just going to be whatever my y value is. This height is just my y. And now I can set up my shell method. And then I would have 2 minus y multiplied by y dy. I did forget to check to find out what my limits of integration should be, so I'm going to do that now. I can really easily see that my lowest y value is 0. My highest y value is at this intersection point. So to find my intersection point, I'll set my functions equal to each other. Divide both sides by negative 2. I get negative x is equal to x minus 2. Subtract x from each side. Negative 2x is equal to negative 2, so x equals 1. And when x is equal to 1, I know that y is equal to 2x, so y is equal to 2. So my limits would be from 0 to 2. And now I can go ahead and integrate. First, I'm going to distribute. That gets me 2y minus y squared. So now I can, that is y squared minus 1/3 y cubed from 0 to 2, which gets me 2 pi times 4 minus 8/3. And my 0 terms are going to vanish. Well, 4 is equal to 12 over 3, so 12 minus 8 is 4 all over 3. So we've got 2 pi times 4/3, which gets us 8 pi over 3. Any questions?
So getting back over things, how come, so for the second function of negative 2x plus 4, that wouldn't x equal y plus 4 over negative 2?
So you're saying x equals y plus 4 over negative 2?
The second function?
So you're trying to find this in terms of x, right?
Yes.
Or I guess in terms of y. So it looks like you distribute it first, so negative 2x plus 4. And then we would subtract 4 from each side, right?
Yes.
And then you're saying divide by negative 2.
Yes.
This is also correct.
Okay.
Because what we can do is we can again just break this down. So I'm going to y over 2. This is the same as y divided by negative 2, right? And then we would have negative over negative makes a positive, so plus 2, which is exactly what I have.
Were you that?
2 minus y over 2.
Oh, okay.
That's my top function. Also right here. Yep. Good?
I think so.
All right. In that case, it's time for another practice problem. In this case, you get to use any method. I'm going to underline that and put an exclamation point for fun. And in this one, I'm actually going to draw out the graph for you. We're rotating it about the y-axis. And I want this region from x equals 1 up till x equals 2. And this bottom curve is 0, and this top curve is 1 over x. Actually, we're going to make it 1 over y. And of course, y equals 0. All right, I will give you guys a few minutes to work through that. And I will say that one method is definitely easier than another here. All right, let's actually just run through this one really quick. So First off, let's talk about how we can decide which method we want to use. In either method, we're going to need some kind of height representation. So we can either use a vertical bar like this, or we can use a horizontal bar kind of like this. Well, one of these is definitely going to work a lot better than another. I'm going to say that a vertical bar is going to work a lot better. Because if we use a horizontal bar, well, a horizontal bar from here, I need to use a different color to make it stand out. If we use a horizontal bar from here up till here, well, that's completely different from a horizontal bar from here up till here. Because this top function is a constant, whereas over here, the top part is a function, is a line, rather than a constant. So then we would need to kind of split it up into two inputs. And I don't want to do that because I'm lazy. So I have decided that I should use a vertical bar, which means that everything should be in terms of x. So my integral should be in terms of x. I should be doing dx's. Well, that automatically tells me that I need to be using the shell method, because here my vertical bar is parallel to my axis of revolution. I don't know if your professor went over how to tell whether you should use like the shell or the washer based on this bar. But basically, this distance here I can represent using a height, but I can't really represent it using a washer. It would be hard to represent this height using a washer. So I'm going to use the shell method. Shell method, yay! All right. So to set up my shell method, I'm going to need the distance from here up till here, which is just my x value, and also the height here. And the height here is going to be my top curve, 1 over y, minus my bottom curve, 0. This is an x equals equation. I want it to be a y equals equation since everything needs to be in terms of x. So since x equals to 1 over y, that tells me that y is also equal to 1 over x. And now I can take my top minus bottom, and that would be 1 over x minus 0, which is just 1 over x. Well, now I can go ahead and set up everything. Another nice hint that we should probably be using x values is we've already got nice bounds for x values. So 1 to 2. And then I have my x, so my radius of a single shell, times the height of a single shell, times 1 over x. And it's super convenient because the x and the 1 over x cancel. That's another reason this one's a lot easier to use the shell method on. Everything cancels nicely. And this comes out to be exactly equal to 2 pi. All right. Perfect.
So wait, wouldn't you technically have integral of 1, and then that 1 would go to x, and then you would just plug in 2 minus 1?
Right.
Just 1?
It would be 2 minus
Okay.
1. So if we wanted to be super formal, we could say that this is 2 pi times x from 1 to 2, which is 2 pi times 2 minus 1, which is 2 pi times 1. But yes, right idea. Now I do have time for one more practice problem, so I'll go ahead and give it to you. Again, I'll go ahead and sketch it out for you first. So in this case, here's a curve, and this is going to be your axis of revolution. This curve is y is equal to sine of x, and coincidentally, I also want this to be the bound. So 2 pi. So I want the area bounded between y equals to 1, y is equal to sine of x, x equals 0, and x equals to 2 pi. Rotated about y equals to 1. So that would be all of this area rotated around y equals to 1. Again, choose a method and then go with it. Good luck.
there only one method that will work? That's the only one that will work. Because number one, I don't know where you get a washer out of that. Number two, my professor told me when you have so say that you're using shell method, you're probably going to integrate based on the x-axis. Yeah, integrate based on the x-axis because you're rotating around something parallel to it. So you can have multiple x values at one y value, which doesn't work.
So you can horizontal.
Yeah.
Right. So I would say that using a horizontal board would be the shell. Because that horizontal board can have parallel to the axis of fusion. Washer is always shell is always horizontal. Or parallel.
Where would you get a washer though? I don't. It's such a weird shape.
So I'll go ahead and give everyone a hint. We want to be using the washer method. Our washer is going to look kind of like this. We're going to take this as a single radius, this distance from here to here. And then when we rotate that around, our washer is going to look kind of like this. So you can think of this as just being a single disc right there.
Didn't it just be this method? Okay.
Remember, the washer method is just the disk method, but expanded. So the disk method is really just like a single part of the washer method. It's the washer method without your lower console, basically.
This is such a weird one to think about.
What?
It's such a weird shape. Just like goes on. Okay.
Should we just go over this one? You want to give it a few more minutes?
No, I think I'm gonna figure out what I did wrong. Oh. This is what you were asking me about at the very beginning. Maybe I do want to go over this because I have no idea how to deal with that.
Sine squared?
Yeah, because the double angle formula what I would change it to would be 1 minus cosine squared. That doesn't help me.
Nope. Try looking for the double angle ones, because we should have a something like cosine 2x is equal to 1, I want to say it's minus sine squared.
There's 1 minus 2 sine
1
squared.
minus 2 sine squared, right.
Oh.
So if we know that 1 cosine of 2x is equal to 1 minus 2 sine squared, we can rearrange this, right? Right?
So you added to the others, yeah.
And then I'm going to subtract cosine 2x and divide by 2. There you have it, right?
That's awful.
Oh, you'll do it loads in integral calc.
Oh, no. They haven't forced me learning yet. I've survived without them so far.
Your life is just so much easier once you give in and memorize them. It's like joining the dark side.
So then the integral is going to be 1 over, or it's going to be 1 minus sine 2x over 2.
Let's see. We'll just go ahead and start working
Yeah.
it out. Since I don't know if I'll be able to keep it. Let's see. So here, this distance here is our capital R. In this case, our lowercase r is just going to be 0. So I'm going to ignore it. Again, I already said we're starting at 0 and going up to 2 pi. We're using the shell method, or sorry, the washer method. So we'll be integrating pi times integral from 0 to 2 pi of just our capital R squared. In this case, our capital R squared would be our top function, y equals to 1, minus our bottom function, minus sine x. And we'll square that times dx, right? Is that the same setup you got?
Yes.
Okay. Now I'll go ahead and multiply that out. That gets me 1 minus 2 sine of x plus sine squared of x. Now, we know how to integrate 1. We know how to integrate 2 sine of x. We just have to figure out how to integrate sine squared of x. And that's where this whole trig identity comes in. I'm actually going to even rewrite this as 1/2 minus 1/2 cosine 2x. So now I've got 1 minus 2 sine of x. And I know that sine squared of x is equal to 1/2 minus 1/2 cosine 2x. And I'm going to also combine my constants. Good? Did you get to here?
No, I didn't, because I was looking over there when you asked me about my setup.
Oh.
So I don't actually have that setup.
Ah. Okay. Well, this is the setup we want.
Okay.
And from here we can just integrate. So the integral of 3/2 is 3/2 x. Here we have plus 2 cosine of x. And then minus 1/4 sine of 2x. All of this goes from 0 up to 2 pi. And I can just plug it in. So this would get me 3 times 2 pi over 2 is 3 pi. The cosine of 2 pi is 1, so 2 times cosine 2 pi is 2. And then the sine of 4 pi is just 0, so I'm going to ignore that term. Now I can subtract our other ones. 3/2 times 0 is 0, 2 cosine of 0 is 2, and sine of 0 is 0. Which gets me 3 pi times pi, or 3 pi squared. All right, well, that's all for today. So thank you everyone for coming, and have a great break.
Look on finals.
Good luck on finals, everyone.